All right, so in the last unit, we learned how to calculate probabilities of random variables. And this unit, we're going to go back again to chapter 2 and talk about transforming, which means moving them around, multiplying or dividing, adding or subtracting by a constant, and combining random variables. And so we're going to describe the effects of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant. We're going to find the mean and standard deviation of the sum or difference of independent random variables. And we're going to find the probabilities involving the sum of differences of independent normal random variables. So when you see normal, you should be thinking of drawing a normal curve. Let go. Here we go. So let's remember back from chapter 2, when you are adding or subtracting a constant, which means you're adding the same number to each observation. So if I said I was going to curve your test by adding 10 points, then you're adding 10, or the constant A, to the measures of center and location. So the mean, median, quartiles, and percentiles. It's not going to change the shape of or measures of spread. It's just going to change the location. And when you're multiplying each observation by a constant, it's the same. It does not change the shape of the distribution. You're just multiplying or dividing each measure of center and location, and you're multiplying or dividing by each measure of spread. So notice when you're multiplying or dividing, you do multiply by the standard deviation. But when you're adding or subtracting, you don't add those numbers to the standard deviation. So let's look at some examples so we can make this real. So we've got this community college, El Dorado Community College, considers you to be a full-time student if you're taking 12 to 18 units. In this case, it would be credits. The total number of units X that a randomly selected El Dorado Community College full-time student is taking in the fall semester has the following distribution. So the probability of somebody taking 12 units or 12 credits is 0.25, 1/4. All right, the probability that a student will take 15 credits is a little higher at 0.30. So we want to find the mean and standard deviation and draw a histogram of this data. Well, as you can see, I calculated it already. But all you need to do is step 1, enter the data into your list by hitting stat enter. Then you go back and hit stat calculate and do your vars stats for L1 and L2 is your frequency. And then we're going to draw a histogram. You can also use your calculator to draw the histogram if you'd like, but you do have to set your window. Your min in this case could be 11 or 12. Your max is 18 or 19. I set it at 19, so I'd have a little space on both sides. And then your Y min and Y max, I just went to the smallest 0, and I went a little bit higher than the largest 0.4, and I scaled it at 0.5. And when I did this, this is something like what my histogram looked like, where my number of credits are down here, and then my probabilities are on the y-axis. Okay, and then you can calculate your mean and standard deviation. So again, the mean is 14.7, so it's somewhere around here. And your standard deviation is 2.1, which is somewhere around here. Okay? Let's go ahead and, this is just our example. Let's go ahead and practice multiplying our distribution by a number. And so we've got El Dorado Community College. Tuition for a full-time student is $50. So let's say every credit they have to pay $50. So we're going to fill in the distribution for tuition charge. And as you can see, step 1 is to calculate the tuition charges. So you're just going to times whatever the number of credits were by 50. So we've got 600, this would be 650. Then we've got 700, so on and so forth. Okay, so go ahead and fill that table in. Filled in our table of values, and I went ahead and entered the data into list 1 and list 2. And what I found my mean to be was now 732.5. 732.5, and with a standard deviation of about 102.8. 102.8. 8. And then what I noticed was when I was making my histogram, it's going to be the exact same histogram as we had before because my probabilities did not change. What did change was my tuition charge. So instead of labeling 12, 13, 14, I'm labeling them 600, 650, 700, 750, so on and so forth. So what we said is that the shape is not going to change in the histogram or the graph. The shape of the data isn't going to change. What's going to change is that the constant is being multiplied by the data. Okay, so let's look at another example. In this case, you're going to be multiplying each of these by 50 plus adding on a student fee of $100. So this, instead of 600, is now going to be 700. 750. Go ahead and fill in the rest of the table with the data. Okay, and so once I've went ahead and filled in my table, I just went ahead and calculated my mean and standard deviation by putting these numbers, entering the data into a list, hitting stat calculate 1 var stat L1 L2, and I found out that my mean also increased by 100. However, my standard deviation stayed exactly the same as it was in the previous example, because when you add or subtract to a distribution, it does not change the standard deviation. Only multiplying and dividing changes the standard deviation. So you'll see, as in my previous example, the 102.8 stayed the same, but my mean increased. Now, if you look at the original example, what you should notice is that the mean in example number 2, and please remember the numbers aren't going to be exact because I did round to 14.7. I didn't use the exact number. But if you take 14.7 here and multiply it by 50, you should get about 732.5. And if you then multiply it by 50 and add 100, you end up at 832.5. And the same is true for the standard deviation. The standard deviation was 2.1 and our constant was 50. So if you go ahead and multiply 2.1 times 50, you get approximately 102.8. Again, it'll be a little different because of rounding issues. And again, because in this example we just added on a $100 student fee, the standard deviation doesn't change. It stays the same. And again, if I were to draw the histogram, I would just draw this same diagram because my probabilities have not changed. The only thing that's changed is my random X. So this would now be 700, 750, 800, so on and so forth. So go ahead and try this problem. We've got a large auto dealership and they keep track of their sales made during each hour of the day. And so let's say that this X value here is our cars sold during the first hour of business on a randomly selected Friday. So that means you have about 40% chance of selling one car. Based on previous records, the probability distribution of X is as follows. So if you don't sell any cars, it's about a 30% chance on the first hour of business on a Friday. So you're going to first calculate the mean and standard deviation, and then you're going to see what the manager's bonus is if they receive a $500 bonus for each car sold. And then you can calculate the mean and standard deviation. So pause the video and please try this problem. Okay, welcome back. You should have noticed that the original problem, your mean was 1.1 and your standard deviation was 0.943. And for the second problem, you just had to multiply it by 500 to get your new mean value of $550 and standard deviation of 471.50. So the likelihood, that's the likelihood of the amount of money that the manager is going to receive in bonus the first hour of business on a Friday. All right, so these are some notes for you to look at. It's basically what we've been saying, that the shape of the distribution doesn't change. You're just going to multiply measures of spread by the B value, and you're also going to multiply measures of center by the B value. And if you're adding or subtracting, you only add or subtract to the measures of center. It does not change the measures of spread. They stay the same. Okay, so let's put it all together. If you are adding and multiplying to a particular distribution, then you take the mean and you multiply by whatever the constant is and add on the additional. And if you are multiplying and adding by a particular distribution, you only multiply by the standard deviation. And it's by the absolute value because you can't have a negative standard deviation. So let's look at how this looks, scaling a test. So basically, if I told you that a statistics class had a mean distribution of a 17.2 and a standard deviation of 3.8 on a test, that's terrible. So I want to multiply the raw scores by 14 and I'm going to add 10 to each one. All right, so what I'm going to do is I want to know the mean and standard deviation of this new distribution that we're going to call y. So what I would do is I would take 17.2 and multiply it by 4 and then add 10 on. And so when I do that on my calculator, let's see, 17.2 times 4 equals, I get 70, that's more like it. So I get 78, oops, that's a terrible 8.8 as my new mean score. And my standard deviation then isn't going to vary by 3.8. It's going to vary by 3.8 times 4, which is 15.2. And now let's review what we learned in Unit 1. What's the probability that a randomly selected student has a scaled test score of at least 90? And so this is where we're looking at, we got to draw our curve, right? And in the middle, right here is 78.8. And so we want to know a 90, so I would say a 90 is somewhere over here. Okay, and we want to know at least a 90, so that means 90 and greater. So I should be thinking in my mind that I'm going to have to take it away from 1. So what I'm going to do is I'm going to do 90 minus 78.8, and this should be review, and then I'm going to divide it by 15.2. So let's go ahead and type that in our calculators. 90 minus 78.8 equals 11.2 divided by 15.2 equals 0.7368. We always go to 4. Now, that's not my probability, that's my z-score. So then again, I got to go, let's see, where is my z-score? Here it is. And I'm looking at 0.7368. So here's 7, 0.7, let's do 0.73. 0.73, it should be like 0.74. So I'm going to go here to 0.7704. So it's 0.7704. And again, this is the probability below a 90. So I want to take it away from 1 because we know the area under a density curve is always 1. So it'll be 1 minus 0.7704. And you get 0.2296. So basically what this means is that there's about a 23% chance that the probability is 23% that the person, a randomly selected student in this class, is going to have a test score of at least 90. Okay, let's go ahead and look at this example. Read it and see if you can figure out what you would do to calculate the mean. If you were to randomly select a student and from the downtown and their number of units, what's the expected value to be? So if you read this problem, if we selected somebody from the downtown campus and somebody from the main campus, and all we have to do is to figure out how many expected credits they're taking, is just add the mean of the downtown campus, the mean of the main campus, and you get about approximately 30 credits that they'll be taking together.